Okay, so we're going to learn two interesting things today. The first thing we're going to learn about bar bets from 100 years ago, or what I think might be bar bets from 100 years ago, and then I'm also going to teach you how to commit accounting fraud. So those are kind of the two fun things, and we'll mix in a little bit of statistics as we go. So we'll see how this kind of plays out. All right, so where did we leave off last time? We started talking about Fisher's exact test. What's the motivation for Fisher's exact test? Well, we have a contingency table, a 2x2 contingency table, and we said that the usual approach that we use for these tables is to perform a chi-squared test. But the chi-squared test is based on normal approximation. So everything, again, boils back down to the central limit theorem because the chi-squared is constructed by squaring normal random variables. How do normal random variables arise? They arise because we've taken sums, and because of the central limit theorem, sums are normally distributed approximately, therefore their squares are approximately chi-squared, therefore we can use chi-squared. But we can only do that if our sample size is large enough, right? So in 2x2 tables, what we mean by large enough is that the entries, the numbers, the A, B, C, and D in these 2x2 tables are big, okay? And it could be the case in a lot of situations that A or B or C or D are not big, right, for whatever reason. Maybe you're studying a disease or some kind of outcome which is relatively rare and you haven't done a case control study and you just happen to have very few cases of your disease, right? That would be a situation where you might have a small number of entries in your table. And if you have a small number of entries in your table, the large sample approximations that allow us to do a chi-square test are not valid. So we need some kind of alternative. And that alternative is available via this idea of the so-called Fisher's exact test. All right, so here's where the bar bet comes in. So Fisher's exact test is named after Ronald Fisher, or R.A. Fisher, who's one of the biggest names in statistics. He's the one who sort of put the whole idea of hypothesis testing on sort of formal foundation. And about 100 years ago, so in, I think early 1900s or so, he was having a discussion with one of his friends. And of course, now maybe a bar bet would consist of like, hey, I bet you I could chug a gallon of milk or something like that. But at the time, the discussion revolved around whether or not this friend of R.A. Fisher's was capable of identifying when they had tea, whether the milk was added to the cup first or the tea was added to the cup first. All right, so this person claimed that they would be able to tell simply by tasting the cup of tea that the milk was added before or the tea was added before. All right, so R.A. Fisher said like, nah, no way you can do this, right? Like, I don't believe you, okay? So he devised an experiment to test this person, okay? And the experiment he devised was to prepare 8 cups of tea, all right, 4 of which the milk was added first, and 4 of which the tea was added first, okay? And he presented these cups of tea to this person and said, I want you to tell me which 4 out of these 8 have had the milk added first, and which 4 out of these 8 have had the tea added first, all right? So the null hypothesis for this experiment, of course, is that this friend of his is full of it, right? And isn't going to be able to identify which of the cups have milk first and which of the cups have tea first, right? But there still needs to be a procedure in place for ascertaining whether, given the number of cups that this person has identified correctly, whether they've identified that number correctly just due to chance, they got lucky, or whether it reflects some kind of real skill, all right? And so in order to devise that evaluation procedure, he came up with this idea of the so-called Fisher's exact test. Okay? So let's think a little bit about what the outcomes of this experiment are going to look like. I'll just switch over here to the camera. So for an experiment like this, we can write down a 2x2 table. Okay? So on the x-axis here, we have the truth, all right, and this would be milk added first or tea added first, right? And then up here you can have the guess, right? This is what the person guessed. Did they guess that milk was added first, or did they guess that tea was added first? Okay, so a couple of things to note about this. If we think about, never mind the entries in the table, let's think about the margins of the table first of all. All right, so what will the margins be here for the truth rows? So what's the total number of cups prepared with milk first? 4, right? And what's the total number prepared with tea first? Also 4, right? Because we said that there are 8 total. What about the column margins? So remember, in this particular experimental setup, the person was told there are exactly 4 cups prepared with milk and exactly 4 prepared with tea. So a rational strategy would presumably be to give a guess of 4 numbers between 1 and 8 as the cups that have the milk in them. Okay, so we can assume that not only are the row margins 4 and 4, but the column margins also have to be 4 and 4. Okay? Now, given those margins, is there still uncertainty about what the entries of the internal cells are? Yes, right? Because there's different arrangements of those internal cells that could lead to having those same margins, right? So for example, if this person really did have this ability, right, they potentially could guess everything correctly, right? Which would mean they'd have 4 here, 0 here, 0 here, and 4 here, right? Or if they were anti-skilled, right? If they had things reversed, they could be 4 here, and 4 here, and 0 here, and 0 here. But of course, there's lots of other arrangements that could lead to the same margins. Okay. So the idea of Fisher's exact test is to say, given the margins of the table, all right, how uncommon is it to see what I saw? Well, how likely is it to see something as or more extreme in terms of the arrangements of the cells, given that my null hypothesis is true? So let's go back to, I kind of wish I hadn't crossed the original things out, but let's go back to that situation where we had 4, 4, 0, 0. So suppose that the outcome of the experiment is the person does actually get all 4 right. Okay? So how would you figure out a p-value for that result, right? So what's the probability of seeing a table as or more extreme than this, given that the null hypothesis is true, given that the person was, if the null hypothesis is the person is just selecting randomly, right? What's the probability of being as or more extreme than this? So if we see the person got everything exactly right, then is there a result more extreme than this? This is in some sense the most extreme result that you could see. Okay? Now, how many ways are there to get all 4 guesses or all 8 guesses right? There's only one way to do that, right? You have to get everything right. Now, how many ways are there to get 3 out of 4 right? No, there's more than that, right? So think about the ways that you could get 3 right. You could guess the first, second, and third indices right, the first, second, and the fourth, right? The second, third, and fourth, right? So there's actually 3 ways, right? The first, third, and fourth. So there's 4 ways that you could guess 3 out of 4 correctly, all right? And then you can go on to say how many ways are there for you to get 2 right. How many ways are there for you to get 1 right, 0 right? Okay, so for 0 right, how many ways are there for you to get 0? It's also 1, right? Okay, so it turns out that you can actually count. If you had enough time on your hands, you could work through all the various combinations, and you could count up the total number of different rearrangements that are possible within these cells. All right? And if you do that, it turns out that the total number of possible arrangements is equal to 70 for this particular table. Okay, so with these particular margins, right, 4, 4, 4, and 4, all right, there are 70 possible rearrangements of those internal cells. So now, back to the question of how do you calculate a p-value. If there's 70 possible arrangements of the internal cells, and we've said that we have one arrangement, which is this 4004, this perfect result, which is the most extreme result, then what would be one way of calculating a p-value? Right, 1 over 70. Right, so 1 over 70 would be a way of saying, well, I see one result out of 70 possible rearrangements that is as or more extreme as what I saw. All right, so indeed, in this case, your p-value would be 1 over 70, which is something like 1.4 something. 0.014. Something. So, if your significance level was 0.05, and you said you were going to reject the null hypothesis if the p-value is less than 0.05, that if this person did indeed guess all 4 or all 8 correctly, right, then you would reject the null hypothesis and say, yeah, all right, kudos, maybe you do have this ability to distinguish between milk first or tea first, right? Maybe you shouldn't be wasting your talent on something as trivial as that, right? So this is the idea, the basic idea of the Fisher's exact test. We fix the margins, and we say, given those fixed margins, how many different possible rearrangements are there of the internal cells in the table? And then of all the possible rearrangements, how many of those rearrangements are, in a sense, as or more extreme than what I saw? They're more imbalanced against the null than what I saw. Okay, so that's the basic idea of the Fisher's exact test. Now, the number of possible rearrangements using something called the hypergeometric distribution. Okay, so the hypergeometric distribution gives you a way to bypass some of these calculations. Okay, so that you can figure out how many different ways there are of taking, say, how many different ways are there to get 3 correct results out of 8 versus 2 versus 1. That can be worked out using this hypergeometric distribution. But you still have to count all the possible rearrangements, and you still have to work with all of these numbers. And so this shows how come the Fisher's exact test, even though it is in a sense exact, so the reason we say it's exact is because when we're counting these rearrangements, we're not using any approximations, right? We're literally counting, we're enumerating all the possible ways that the data could be arranged. It doesn't matter whether the sample size is large or small, this is going to be a valid approach. But when the sample size is large, which means the margins are big, right? Now, if you start counting all the possible rearrangements, there can be a lot of possible rearrangements, right? What if we had done an experiment with 100 cups of tea, split 50-50, instead of 8 cups of tea split 4-4? Well, now if you figure out, suppose the person got, out of those 50, they got 41 out of 50 right. Well, now, in order to figure out the p-value, you have to say, well, how many different ways are there of getting 41 out of 50 correct? And then you have to say, well, a more extreme thing would be getting 42 out of 50 correct. So now you have to count all the number of ways you could select 42 correctly out of those 100, and 43, and 44, and 45, and 46, and 47. And you have to count all those different enumerations for all those different possible scenarios, right? So as the sample size gets bigger, as the margins get larger, it becomes computationally more and more challenging to actually carry out a Fisher's exact test. And furthermore, as we make the sample size bigger, what do we know about the chi-square test? It's getting better, right? It's getting more, the approximations are getting better, the central limit theorem is kicking in more, and we're more comfortable using the chi-square test when the sample size gets larger. So when you have small sample sizes, that is where the chi-squared is bad, the Fisher's exact test is always going to be exact, and when sample sizes are small, it's usually relatively fast to compute. When sample sizes are big, theoretically, there's nothing stopping you from doing a Fisher's exact test, but computationally, it's a bit of a pain. Now, with modern computers, what constitutes like a big sample size that's going to make Fisher's exact test a problem? You know, it used to be that like, well, don't do a Fisher's exact test if you've got more than say like 100 things in your cell. Nowadays, I mean, you're probably talking about, you know, cell entries in the tens of thousands before a computer is going to take more than, you know, half a second to do this. Okay, but still, you know, for large tables, we conventionally just do a chi-square test just because we know the approximations are good, and the p-values are going to start to coincide once you get to about, you know, 10 or 20 entries in these cells. The difference between the p-value you compute using a Fisher's exact test and the p-value you compute using a chi-square test is essentially going to be irrelevant. Okay, it's going to be too small to matter. All right. Any questions about that? All right. So that's the Fisher's exact test. Fun fact. So there's actually a I think I put a link to the lady tasting tea, so-called lady tasting tea experiment on Wikipedia here. So there's just a slightly updated version of the notes, which has a couple of new things in here, including this. Also, fun little fact: the Wikipedia article on the Fisher's exact test has this exact table in it, except it talks about students taking a statistics exam, whereas somebody, I guess, decided for a biostat class that this was going to be about like dieting behavior by sex. So clearly this is not real data, right? Somebody just made this example up and maybe even pulled it from the Wikipedia page and just changed the labels for the exposure and the disease. Anyway, so I was reading through the Wikipedia page on Fisher's exact test, and I'm like, that table looks awfully familiar. Where have I seen that before? And then, of course, you know, here it is. All right. So if you actually do this in R, the command in R is fisher.test. So you give it this table. This is a way of sort of creating the table. You've got the first row, which is 1 and 9. The second row is 11 and 3, as we saw back here, right? 1, 9, 11, 3, the entries. Of course, when you're doing this in statistical software, you don't need to give it the margins, right? Software can add. It can figure out that 1 plus 9 is 10, 11 plus 3 is 14. You don't need to do that yourself. You just give it the numbers in the table, right? And then it's going to carry out this Fisher's exact test. It's going to go through, look at all the possible arrangements that are more extreme than the 1-9 imbalance that we saw. Okay, it's going to say, well, the alternative hypothesis is the true odds ratio is not equal to, this is kind of running off the screen, but the true odds ratio is not equal to 1. It's going to give you a 95% confidence interval for the odds ratio. It's going to say the estimated odds ratio is 0.04. And as I said, the p-value is what we're kind of really looking for, which is 0.003. Okay, so it just counts all the arrangements and says how many arrangements are more extreme than what we saw. In SAS, same idea. Here's just inputting the data. Okay, proc freak. You ask this sort of /exact thing for these tables, and then you're going to get a similar output from SAS for the Fisher's exact test. Okay, if you don't ask for this exact test, you're probably going to get a chi-square test. Different software packages often will warn you if the number of entries in your table are smaller than 5. So for example, you can ask R to do a chi-square test on this table. But what it's going to do is it's going to warn you and going to say, beware, the chi-squared approximation may not be very good because the number of entries in the cell, some of them are less than or equal to 5. SAS will do the same thing. So it's not going to prevent you from getting a p-value, but it's going to tell you, like, maybe you shouldn't be using the chi-square test. It's kind of funny, right? Because most times software packages will not do anything to kind of check whether sample sizes are big enough. So for example, if you're doing a t-test, most software does not warn you if you try to do a t-test for like 3 versus 3, right? It'll just it'll spit out the p-value. But for some reason, they've decided that the rule of thumb of having number of entries in these tables less than or equal to 5 is sort of a solid enough rule that it can actually base advice to you on that rule. Okay, so it's one of the few situations where statistical software will actually complain to you about the data you're giving it when it carries out a test, if it thinks that the test may not be appropriate. So 99% of the time, software is not going to say anything to you about what you're doing, and it's up to you to do the appropriate test. Here it's going to give you a little bit of help. If you sort of enter a table and you try to do a chi-square test, it's probably going to warn you and say, maybe this isn't such a good idea. Okay? So as I mentioned, of course, you can always do a Fisher's exact test, but it's going to get slower as the sample size increases, the number of entries in the cells increases. And of course, the distinction between the Fisher's exact test and the chi-square p-value gets essentially negligible and irrelevant as the sample size gets bigger. Okay, so the rule of thumb, as I said, as software recommends, is you should use the exact test if any of the entries in the table cells is less than 5. Okay, so everything we've dealt with so far has been for 2x2 tables, right? Yes, no exposure, yes, no disease, right? Yes, no treatment, yes, no, whatever your outcome is. But of course, there are a lot of situations in which you want to arrange your data with more than 2 rows and more than 2 columns. So here's a perfect example. Here we have the result from a randomized trial where the outcome was the occurrence of an MI, a heart attack, okay? And there were 3 treatment groups, a group that received aspirin, a group that received statins, and a group that received placebo, okay? How do I know this was a randomized trial? Well, I'm just guessing based on the fact that these totals are very similar. So I'm guessing these arose because it was decided that there would be approximately 11,000 people recruited to each of these arms, right? Now, interesting thing to note here, how come we needed 11,000 people in each of these groups? How come we needed like 30,000 people in this study, right? That's a really big clinical trial, right? How come we needed the sample size of 30,000 or so? Sorry? Yeah, right. It has to do with the fact that MIs don't happen that frequently, right? So I don't know exactly what population the study was conducted in, but supposing it was conducted in a relatively sort of general population, the MI rate over 1 year, over 5 years, or over how long the study went is not that high, right? As you can see from here, there were only a total of 400 MIs out of a total of 33,000 people enrolled in the study, right? So that event rate's like what? Like 1.3% or something like that. So that's not a very high rate. And, if we'd had a sample size of 3,000 instead, then with only 40 approximately MIs to go around, it might have been very hard to see whether there were any differences between the aspirin group, the statin group, and the placebo group. Okay, so for these rare outcomes, when we're doing a clinical trial, we have no way of getting around the fact that we need a large sample size, right? Now, we talked before about a case control study, right? How you could do a case control study, and if you were interested in assessing the effects of statin and aspirin, versus getting nothing, you could have carried out a case control study and taken people who had MIs and people who didn't, and then compared whether or not they'd taken statins or aspirin. But what's the limitation of that design compared to this? Right, so when we're doing a clinical trial, right, the beauty of randomization is that by virtue of having randomized people to these groups, we know that on average, the people who receive aspirin, the people who receive statin, and the people who receive placebo are on average the same, okay? The characteristics of those people are balanced between the groups. So there aren't systematically more women on aspirin versus a statin. They're not systematically older or younger. They don't have aren't more prone to diabetes or anything like that. So anything that we can measure and anything that we can't measure is balanced by virtue of randomization. So the benefits of randomization, right, is that we can actually start to say, well, if we see that, aspirin has a lower rate of MIs than statin and placebo, that probably reflects the fact that aspirin is actually protective against MI, and it's not just the people who happen to take aspirin tend to get fewer MIs, right? So we can actually make sort of a causal conclusion that we might not be able to get out of a case control study, right? Obviously, case control study, we could sample a lot fewer people, it would be much more efficient, but we lose the ability to make the sort of causal interpretation of our result, okay? All right, anyway, so the point is, this is no longer a 2x2 table, right? This is a 3x2 table for the 3 different treatment groups that we have. We still have 2 columns, but we now have 3 different exposure groups. All right, so the question is, what's our null hypothesis here? Well, a reasonable null hypothesis is that aspirin, statin, placebo, who cares? They're all the same, right? That's the null. So before, when we had exposure, yes, no, we said the null hypothesis was that exposure had no effect on the probability of disease, right? Here we're saying the same thing, right? Exposure has no effect on the probability of disease, but now we have multiple levels of exposure, so it's essentially saying none of the levels of exposure has any effect on the probability of disease. So if we write down P1 to be the probability of MI if you take aspirin, P2 as the probability of MI if you take a statin, and P3 is the probability of MI if you get the placebo, then the null hypothesis is that all 3 of those probabilities are equal, right? Nothing works. Now, based on what you see here, do you think that there is evidence against that null hypothesis? Just if you were doing a gut reaction. It kind of looks like it, right? I mean, the rate of MI among people who got the placebo compared to aspirin is almost twice. So that seems like we probably have fairly substantial evidence here against that null hypothesis that the rate of MI is the same regardless of these groups. Of course, we have to be careful here with these numbers because we can compare these numbers directly because the totals are the same. If these totals weren't different, then we couldn't obviously compare these numbers directly. We'd have to divide by the totals to get a rate, etc. All right. So the key thing is that if we set up our null hypothesis that all of these probabilities of disease are the same, right, regardless of exposure, then that is a very strict null hypothesis, right? And what I mean by that is that if you think about what exists in the alternative, any situation in which all 3 of these probabilities are not the same is in the alternative, right? So even if aspirin and statin are the same, right, but one of those is different or they're both different than the placebo, that's in the alternative because they wouldn't be the same. Or if statin and placebo are the same but aspirin's different, that's in the alternative, right? So any departure from this strong null hypothesis of P1 equals P2 equals P3, they're all the same, any departure from that lies in the alternative, okay? So when we reject the null hypothesis for a contingency table with multiple levels of the exposure in this case, we have to be very careful in saying that all we've done is rejected this very strong null that all of these levels are the same, right? That these exposures have no effect on the outcome, all right? It doesn't mean that they're all different, right? That's the key thing to remember. All it means is that they're not all the same, right? Now, of course, in a 2x2 table, the fact that exposure, that the effect of exposure on disease is not the same for these 2 exposures is the same thing as saying that they're not the same. So it's rejecting the null in a 2x2 table is the same thing as saying that there is an effect of one, that the exposure effects are different, right? But of course, in this situation, rejecting the null just means there is at least one level of the exposure for which the effect is different. Okay? Doesn't mean that they're all different. All right, so we can rephrase this as the disease and the treatment are independent versus the disease and the treatment are not independent, right? And this notion of independence, just like in the 2x2 table, this idea of independence allowed us to derive expected entries in the cells. We're going to have the exact same thing here, right? So the statement of the null hypothesis for a R by C contingency table that's bigger than 2x2, the statement of the null hypothesis is the exact same as it was in the 2x2 table, right? Disease and exposure are independent. right? That's going to imply different things in the cells for a bigger table, but the statement of the null hypothesis is the same. So how do we actually go about calculating expected numbers in these cells, right? Now, what does it mean? Let me go back to here, okay? Let me draw another table. And I'm going to go back to a 2x2 table here quickly. Okay, yes, no. Okay, so let's see if I can get that a little bit higher. So if E and D are independent, then what is true about the probability of E and D both happening at the same time? What does that equal to? Right, so we can multiply the probabilities together. So if you want to remember why that's the case, think back to coin flipping. If we flip a coin twice, right, what's the probability we end up with two heads? It's a quarter. Why? It's a half times a half. A half because the probability of heads on the first flip is a half, the probability of heads on the second flip is a half, and since the flips are assumed to be independent, we can multiply a half by a half to get a quarter. Okay, so the same thing. When we have independence, the definition of independence is that the probability of two things happening is the product of the probabilities of each of those two things happening separately. Okay, that's the definition of independence. An alternative definition, which we can also sort of think about, is that the probability of disease given exposure and the probability of disease given not exposure are the same. That's the same. That works out to be the same thing. That's also a definition of independence. But for our purposes, we're relying on the fact that the probability of two things happening is the product of their probabilities. Okay? So now, if we want to work out what's the probability of falling in the cell that we've labeled A, okay, if our observations are independent, okay, then, so the probability of falling in cell A, okay, I should probably just, this would be an easier thing to do. Oh, look at that. Oh, now it's going to fall down, isn't it? Well, let's hope that stays up. Okay, the probability of falling in cell A is equal to what? So what probabilities can we multiply together to get the probability of being E is yes and D is yes? E is A over A plus B, right? That's the probability of being, that's the probability of being diseased, right? So we have A over A plus B, right? 1 second. What am I doing here? Sorry. My mistake. Okay, we're looking at the margins, right? Okay. Looking at the margins, the probability here is of being exposed is A plus B over N, right? The probability of being diseased is A plus C over N, okay? So therefore, this probability is equal to whatever this is, right? So A plus B times A plus B times A plus C divided by N squared, right? But that's not the formula that we talked about last time, right, on Monday for getting the entry in the cell, how come we end up with an over n instead of an over n squared in the formulas that we saw? Right, to the expected value. So we don't want the probability of being in that cell. We want the expected number in that cell. So if the probability of being in that cell is a plus b times a plus c over n squared, right? Suppose the probability is 0.07, right? And we have 100 total observations in the table, then how many actual observations would we expect in that cell? Well, we'd expect 0.07 times 100, right? So in this case, in order to get the expected number, right? So therefore, the expected number is equal to a plus b times a plus c over n squared times n, which is just that formula that we saw before. Okay? So it comes from the definition. Everything goes back to the assumption of independence. The null hypothesis is that exposure and disease are independent. That implies a particular way to calculate the probabilities of falling in each cell, and then you convert that probability into a number just by multiplying it by the total number of observations in the table. Okay? So that's where these formulas come from. Now, what if we have a contingency table that now has 3 rows instead of 2. Okay, so now we have exposure 1, 2, 3, and then like disease, yes, no, and then we're going to use the letters A, B, C, D, E, and F. Okay, so the margins here are A plus B, C plus D, and E plus F. What are the margins here? This is A plus C plus E, and this is B plus D plus F. And we're still going to call the total number N, right? Now, null hypothesis, same as we had in the 2x2 table, right? The probability of a particular exposure level and disease is equal to the product of their 2 probabilities, right? So therefore, what is EA? Well, EA is going to be marginal on the rows, A plus B, times, what do we think? Marginal on the columns, which is what? A plus C plus E, right? A plus C plus E, right? Divided by N, right? We can play this game all day. EB is A plus B times B plus D plus F over N, etc. So we can work out EA, EB, EC, ED, EE, EF. So there's 6 entries in the table, and there's 6 expected values that we can calculate under the null hypothesis that we can correspond with those values. All right? And what was the idea of the chi-square test in the 2x2 table? What was it based on? So we have observed entries and we have expected entries. Yeah, so how did we go about doing the chi-square? Not directly. Not directly. We're going to calculate a test statistic. So what did the test statistic look like? What did the test statistic measure? The what? Yes, but what did it actually measure in terms of the entries in the table and the observed entries and the expected entries? The difference, and more specifically, the square difference, right? So we're looking for the distance between the observed entries, the A and the B and the C and the D, and the expected entries, the EA, the EB, the EC, and the ED, right? If the observed and the expected entries are close to each other, and we calculated the expected entries under the assumption that exposure and disease were independent, then that tells us that the observed entries are probably consistent with independence, right? That's the concept of that chi-square test in the 2x2 table, right? So what about in this larger table? Well, the logic extends exactly. The only difference now is instead of adding up observed minus expected squared divided by expected for 4 different cells, like we did in the 2x2 table, the chi-squared statistic now involves observed minus expected squared divided by expected in how many different cells? 6, right? So now we're just adding numbers across 6 cells as opposed to adding numbers across 4 cells. Okay? Now, what do you think is going to happen? So when we did the 2x2 table, we calculated this chi-squared statistic, okay? And does anybody remember what the number of degrees of freedom was for the chi-squared that we used? 1, yes. 1 degree of freedom for the chi-squared for a 2x2 table, okay? And Eric talked about on Monday how when you have these larger tables, the number of degrees of freedom is different than it is for the smaller tables. Does anybody remember what the formula was? Right, R minus 1 times C minus 1. So in this case, that would be what? So we're going to have a chi-square statistic with 2 degrees of freedom, which we should use as our reference distribution, instead of a chi-square statistic with 1 degree of freedom. So it's the same idea as in the t-test, right? In the t-test, we needed to calculate the degrees of freedom on the basis of the sample size, right? So if we had a particular sample size, you might have a t-distribution with like 8 degrees of freedom, or one with 17 degrees of freedom, or 77 degrees of freedom, which was, as we said, was essentially a normal distribution. But here, we're going to use different degrees of freedom for different chi-squareds. And as our table gets bigger, the number of degrees of freedom that we're going to need to use in our chi-squared gets bigger as well. Okay? Now, I want to show you something. So let's just actually quickly go through this before I show you something here. All right, so this is the formula. The formula for the chi-square statistic is the exact same. The only difference is we're now adding 6 things up instead of 4 things up, and we have to change the reference distribution to a chi-squared with 2 instead of 1 degree of freedom. Okay? So the p-value here, well, if we calculate this chi-square statistic, we end up with 25.1. And it turns out that if we calculate using software the probability that a chi-squared with 2 degrees of freedom exceeds 25, it's small, and so there's strong evidence to reject the null hypothesis of independence between treatment and MI. All right? But what does that mean in this context, right? We have aspirin, statin, and placebo. So what have we concluded on the basis of this p-value? At least one of them is not equal to the others. We don't know whether it means that statin doesn't work, it's the same as placebo, but aspirin is better, or aspirin and statin are equally effective and they're both better than placebo, or all 3 are different. We can't conclude any of that on the basis of this p-value. All we've concluded is that there is some difference between these levels. Okay? So when probably not in this class, but when you take a class and you start talking about things like ANOVA, which I guess maybe we'll get into a little bit of ANOVA here. When we start talking about ANOVA allows you to then start kind of breaking down the subcomponents and saying, you know, which of the levels are really different from each other. But one has to be careful when following up a significant test with a bunch of additional tests to see which are different. And remember when I talked about this problem of multiple testing? How if you decide to go on testing things on the basis of a previous significance test, you can run into problems. It's the same idea here, right? If you're like, there's a difference between these things. Let's go hunting out for which of the groups are different. Now you run into issues with having to adjust for multiple comparisons. And so some of the techniques which propose to do these so-called sort of post hoc tests involve making corrections to your p-values to account for the fact that you've done this multiple testing. In fact, one of the most, I think, cutely named one is the so-called Tukey's honestly significant differences adjustment, right? To sort of say like, no, honestly, these two things actually are different, despite the fact that I've allowed myself to do this multiple testing. Okay. Anyway, so as we said, for these larger contingency tables, the chi-square statistic has an r-1 by c-1 degrees of freedom. And so we typically can use the chi-squared approach for these tables under a slightly less restrictive assumption than for the 2x2 table, which is that the average expected cell count is greater than or equal to 5, and each expected cell count is greater than or equal to 1. Right? So in a 2x2 table, we require that each entry be greater than or equal to 5. Here, we don't need each entry to be greater than or equal to 5. We just need overall the average to be greater than or equal to 5, and in each cell, we have to have at least one entry. Okay, so cells with zeros are problematic in these larger tables, but it's okay if there's a couple cells that have one or two, as long as some of the cells have larger entries in them. Okay, obviously in the example I gave you, there's no issue at all, right? You've got hundreds and thousands in these tables, but for these tables, it turns out that we don't need to be quite as strict as we do in a 2x2 table. Okay. As we said in the 2x2, we require a bit more conservatively that all expected cell counts are greater than or equal to 5. All right, so here's what I wanted to talk about with respect to the chi-square distribution. Up until now, when we've talked about test statistics, and we've dealt mainly with t statistics and z statistics, we could make a very convenient mental shortcut, which is we could look at the test statistic computed, and we could pretty much conclude, based on its magnitude, whether or not we'd be rejecting the null hypothesis. Right? If you get a t statistic of 15, right, unless your degrees of freedom is like 1, you're rejecting. Right? Because the t distribution, we know the tails are going to stop at, plus or minus roughly 2, right? Maybe with 2 or 3 degrees of freedom, it's like 2.3 or 2.4. But the point is, big values of the test statistic mean you reject always when you have a t or a z distribution. Okay, so we sort of have that easy mental shortcut if you're reading a paper and it says like, t is equal to 17.7. Well, the p is going to be less than 0.01. You don't even need to see the p-value. You know it's going to be highly significant. Okay? Not the case for the chi-squared. Okay? And the reason it's not the case for the chi-squared is what this plot shows you. And what this plot is showing you is 4 different densities for 4 different chi-square distributions, which differ in terms of the number of degrees of freedom they have. So the red curve is the density of the chi-squared with 1 degree of freedom. So we can see that the density starts off sort of very high near x equal to 0, and once you get to about 10, there's almost no probability to the right of 10 for the chi-squared with 1 degree of freedom. All right? The green line is the chi-squared with 2 degrees of freedom, and we see that it's a little bit heavier tailed than the chi-squared with 1 degree of freedom, but it also drops off around 10, right? But it's a little heavier tailed. Now the cyan line here is the chi-squared with 5 degrees of freedom. Now this is starting to get more interesting, right? Because at this point here, say around 7.5-ish, well, the probability to the right of 7.5 under the red or the green line are pretty small, right? So if we saw a chi-squared statistic of 7.5 or 8, and the reference distribution was a chi-squared with 1 or 2 degrees of freedom, we'd probably be saying that p-value would be less than 0.05, right? Because the area to the right of that point is small under those curves. But what about under the cyan curve? Well, there's a pretty decent amount of area to the right of 7.5 under that cyan curve, right? So 7.5 would not be enough probably to reject at a 0.05 level if the appropriate reference distribution for that statistic was a chi-squared with 5 degrees of freedom, right? So maybe if you were doing a contingency table that was, what multiplies together to give you 5, you were doing a 6x2 contingency table, right? Where the appropriate reference distribution is has 5 degrees of freedom, you would need your test statistic to be at least probably around 10 in order to get a p-value less than 0.05, right? And now we can push this even further. Suppose you were looking at a really big contingency table. Maybe it's, I don't know, 6 by 5 should do it, right? 6 minus 1 times 5 minus 1 gives 5 times 4 is 20. Okay, so if you had like a 6 by 5 contingency table, now the chi-squared that you're going to need to see in order to reject is like probably way out here. So it might be, 25, 30 or so. Okay? So the point is, as the number of degrees of freedom increases, the critical value that you're going to need in order to reject at a particular level of significance is also going to get bigger. So there's no easy mental shortcut that just says, oh, well, the chi-squared statistic is 20, therefore reject. Just like, in the t or the z, if the t statistic is 20 or the z statistic is 20, you're rejecting, right? Basically always. Here, you might be rejecting if the number of degrees of freedom is low, but if the number of degrees of freedom is high, you're probably not rejecting with a chi-squared statistic of 20. Okay, so the number of degrees of freedom plays a much more essential role for the chi-squared because the difference between a degrees of freedom of 5 and a degrees of freedom of 20 makes a huge difference in these distributions, right? Whereas for a t distribution, the difference between 5 degrees of freedom and 20 degrees of freedom is the difference between the plus or minus, values being 2.09 and 2.02 or something like that. So they're very similar for the t, but they're very different for the chi-squared. Okay? And of course, as we said, as the number of degrees of freedom for the t increases, what happens to the shape of the distribution? It approaches a normal. What happens as you increase the degrees of freedom in the chi-squared? And it just keeps moving further and further to the right. It doesn't approach some common distribution. Okay, it's just going to keep on. If I did 50, the curve would be even more shifted to the right. Okay, so there's no notion in which, oh, well, if the number of degrees of freedom is really big, that it's essentially just something. It's not. Right? It's its own thing that you need to contend with.
Wouldn't it get towards with the central limit theorem, it would get towards its central value, so you wouldn't go all the way to infinity, you would centralize.
For the chi-square?
For the chi-square, yeah.
No. No. So the chi-squared is going to keep moving to the right. Right? The central limit theorem has to do with the fact that sums in the limit are normally distributed. Right? So the distribution of sums, right, sums, is going to eventually resemble this bell shape. The chi-squared is not the distribution of a sum. Remember, the chi-squared arises as the square of a normal. That's the reason it's only positive, right? So we don't have this approach to central tendency, right? As we have larger and larger numbers of things that we're summing together, the distribution of those things will be approximately normal, okay? And those normal things, if we square them, will be individually chi-squared, but then if we add up more and more of those chi-squared things, we're going to push further and further to the right as we get more and more degrees of freedom. Make sense? Okay. Yeah?
I'm wondering what the benefit of doing a table with 20 degrees of freedom would be. Is that something that's done commonly? Because your null then would be
that everything's the same, and it's a very uninteresting null hypothesis to reject, right?
Right, yeah, and I'm also thinking too, if you had two things that were different and then the rest were the same, it could still
that would be in the alternative. So, yep, you could easily reject on the basis of everything being the same except two cells.
Okay.
So yes, absolutely, yes. There's no question that as the number of levels of the exposure and of the disease increase, the usefulness of the p-value rejecting the null gets smaller. It's less and less useful because, yeah, we'd expect there to be some difference between these groups, so between some levels of these groups. So the fact that there is some difference doesn't tell us very much.
So realistically, it's mainly using the 2x2 types.
Yeah, 2x2. I mean, sometimes you end up with these 2x4 or something like that situations, but
you just do a lot of them.
You could, right? I mean, that's something that you could do as well, because that's going to at least tell you which of the things are actually different. But then you run into this multiple testing issue if you use that approach. So there's no easy, perfect solution, right? So you can either combine everything and do this perfect one p-value omnibus test, but as you mentioned, the null is pretty uninteresting as you start to add more levels of the exposure, more levels of the disease, because you're looking for complete homogeneity across all the different dimensions, right? Or you could break it down and do these things separately, but now you run into the problem that you've got now like 10 p-values, and you have to figure out like, well, one of them is less than 0.05, so does that mean that's really less than 0.05? Like, should I really reject? And so you run into the problems from that perspective. Yeah. No free lunch, right? All right, so let's take a quick break. Let's come back at 1:15, and we'll talk about how to cheat on your taxes. Okay, so I'm going to point out, but not actually go through. This is a quick example with outcome. This is the outcomes on the rows, exposures on the columns, but you could just transpose it if you want. For 4 levels of exposure, 2 levels of disease, and you can go through and carry out the same kind of things we did before with calculating expected entries in this table, calculating a chi-squared statistic, etc. So I'm going to let you go through that yourself if you'd like to, so that we can get to talking about taxes. Right. All right, so let's pull that up. Oops. Okay, Benford's law. So what do the following data sets have in common? Population of countries around the world, number of Protestant Christians per country, Twitter users by followers count, people killed by terrorism, distance of stars from Earth in light years, most common iPhone passcodes. Well, here I'll tell you what they have in common. So way back, about 130 years ago, somebody by the name of Simon Newcomb was going to the library, as people used to do when they needed to look up things like logarithms, right? Of course, there were no calculators with a log button at the time, so if you needed to know like what the log of 172 was, you needed to go to a book, okay? And it turned out that when he went to the library to look at these giant books of logarithms, he noticed that the logarithm tables were more worn at the beginning. So for numbers that had a smaller number, for the low digits, right? So these books were arranged by digit, right? So you look for like, 1, 10, and 100, et cetera, would be on the first 2 pages, and then you'd have 2 and blah, 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 further and further. And he noticed these books were more heavily thumbed at the beginning than at the end, okay? And building on this, about 50 years later, so in the 1930s, late 1930s, Frank Benford, a physicist, sort of derived what was known as Benford's law. Okay, so what is Benford's law? Benford's law has to do with the distribution of the first digit in so-called naturally occurring numbers. Okay, so just numbers that arise from some kind of process, right? So all those data sets that I gave the example of, populations of countries and Twitter users by number of followers, et cetera, like those are just sort of numbers that arise, okay? They're not from a designed experiment to get particular values. They sort of come up naturally. And if you look at the distribution of the first digit in those naturally occurring numbers, you would think that those first digits would be uniformly distributed, right? You're equally likely to see a 1 as a 2, as a 3, as a 4, blah, 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 all the way up to 9. But it turns out that if you actually look at these naturally occurring data sets, the distribution of the first digit is distinctly not uniform. In fact, it looks something like this. So approximately 30% of naturally occurring numbers start with a 1. About 18% start with a 2, 13% start with a 3, and so on and so forth, down to only about 1 out of 20 so-called naturally occurring numbers starts with a 9. Okay? So you probably don't believe me, right? This seems like, no way, this can't possibly be true, all right? But turns out the rule is something like log 10 of 1 plus 1 over d, where d is the first non-zero digit, okay? So if you don't believe me, then we can look at some examples here. All right, so here are some actual data sets. And plotted for those data sets is the number of things with these leading digits. Okay, so this is the distribution of the leading digits, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's the data set Twitter uses by followers count. All right, you'll see that about 30% have a 1 as the first digit, 17% have a 2, right, and so on and so forth. So this is clearly not uniform. All right, most common iPhone passcodes. What else are we going to look at here? Population of Spanish cities. What else are we going to look here? 2007 population per district in Peru. So I could go for this for a while. Brazilian addresses, street numbers. Right? And so these are real data sets, right? These aren't just made up, right? Somebody's actually collected data on these things. And there's just a ton of things here. Forcibly displaced populations from 1994 to 2008. All right? So this law is actually remarkably true in a wide variety of these so-called naturally occurring numbers, right? You're much more likely to see 1s and 2s and 3s as the leading digit than 7s and 8s and 9s. Okay. Why is Benford's law true? I don't know. I don't really have a good idea for why. But it turns out to be the case. Okay, there's probably people who have thought about it and who might be able to figure out why it's the case. But I really don't have a good explanation. But it appears to be true, valid. Okay. So here's where we get into the stuff which I should stop recording because I'm going to tell you how to cheat on your taxes. No, I'm just kidding. I'm not actually going to tell you how to cheat on your taxes. But Benford's law isn't just a fun thing to play with all these data sets. It's actually been used to detect fraudulent accounting practices. How can we use to, why is it that we can do this? Well, it relies on the fact that people don't necessarily know Benford's law, right? So now all of you know Benford's law, which is why it's going to enable you to avoid this kind of mistake if you're planning on committing accounting fraud. But when human beings try to create quote unquote random looking entries, they're going to tend to create numbers whose first digits are uniformly distributed, right? They're going to tend to say like, well, it doesn't make any sense for me to have 30% of the numbers start with a 1. That doesn't seem random at all. It should be much more random if 1/10 of the numbers start with 1, 1/10 start with 2, 1/10 start with 3, etc. Okay? So it's people when they're making things up, when things are not actually arising from some kind of natural organic process, those first digits are not always going to be equally likely. Those first digits are going to tend to be more equally likely than if the data actually were true, right? And they actually followed this law. Okay. So what I have here is, suppose that an administrator was processing some claims from faculty members who had submitted a bunch of expenses for travel to conferences. Okay, so these are $100 amounts for expenses that have been submitted. Okay, and maybe there's some suspicion that the person or the people who submitted them these may not all be legitimate, right? They may have made up some of these expenses, right? That they didn't actually do these things. They didn't do the things they said they did. They didn't take those plane rides, whatever. They didn't go to those restaurants. They didn't pay that conference registration fee. And they're submitting these false claims. And they made up these numbers, okay? So the question is, how do we assess whether or not the prices are real, right? These are actual prices, these are actually expenses that arose, or that they were fabricated. Yeah.
Using Benford's law.
Okay.
So if there's
Wow,
more numbers,
that's so insightful.
If there's more numbers that start with smaller single digits,
Okay.
then it's likely.
Okay. So how do we operationalize that?
You take your count of the first one.
Okay. So we're going to start by counting the number of digits that start with a 1, the number of digits that start with a 2, the number of digits that start with a 3, etc. Right? So we could get something like this, right? So it turns out if we actually summarize those numbers, we get that set of entries. So we could eyeball that and say, well, I don't know, does that look like it follows Benford's law? Not so much, right? We wouldn't expect to see that many 7s and 8s and 6s. We'd expect to see more in the 1s and 2s and 3s. But we're not in a class where we've made our money from saying, I eyeballed it and it more or less looks like, we should reject the null hypothesis that this sort of follows the law. So what have we recently learned? What technique have we talked about that might actually enable you to assess formally whether or not these entries follow Benford's law? Chi-squared test. How come? How could we apply the chi-squared test here?
What are the actual unexpected values?
Right? So that makes sense, right? We've got observed entries in each of these 9 cells, right? And based on the fact that we have 100 total entries, we could say, well, Benford's law says that we'd expect 30% of the entries to have a leading digit of 1, 18% to have a leading digit of 2, whatever, it's 13% to have a leading digit of 3, etc. And if we had 100 numbers, that tells us the expected number that we'd expect to fall in each cell, right? So if the data were actually naturally occurring and following Benford's law, we'd expect to see like 30 to have a leading digit of 1, which is 0.3 times 100, right? 18 to have a leading digit of 2, etc., etc. Okay, so we can work out the expected number in each cell, and we now have the observed number in each cell, and we could apply a chi-squared statistic to assess the difference between expected and observed. So there's an actual name for this procedure because this is not a contingency table, right? It's got one row in some sense, right? All we're doing is we're tabulating the different values. So what this is actually known as is it's actually known as a goodness of fit test, okay? It's a really awkward, goodness is a very odd way of putting it. It's, shouldn't be called the wellness of fit test or something, but anyway, the goodness of fit test. How good is your fit, right? And so what you're trying to do is you're trying to assess, again, the match between the observed frequency, right? This is the number of observations that start with a 1, with a 2, and the expected frequency if the data actually did follow Benford's law, right? So 30, 18, 12. This is just conversions of the probabilities that I showed you earlier into numbers by multiplying by 100, because we have 100 total numbers that we collected. Okay? So then we apply the exact same chi-square statistic as we did in the contingency table. We just add up all the cells. We say observed minus expected squared divided by expected, and we'll add those up over these 9 cells. Okay? Now, if we add up over these 9 cells, what do we think the total number of degrees of freedom is going to be for our chi-squared statistic? Any guesses? Is it 1? Do you think it's going to be 1? Why not?
Because we have 9 columns.
Yeah, so we're adding more than, we're adding a bunch of things together. Okay, so it's probably not 1.
So it's probably
Could be 9, right? Could be 8, right? Why would we tend to vote for 8 over 9? Right, it's minus 1, right? We subtract 1. Okay, so the answer is 8. Okay, the appropriate reference distribution is a chi-squared with 8 degrees of freedom. And the way that you could think about why this is 8 is because the number of degrees of freedom sort of reflects the total number of values that you have to play with. So if you think about it, if I have 100 total observations and I've told you the entries in 8 out of the 9 columns for this table, the 9th is no longer subject to random variation, right? It's determined by the other 8. It's 100 minus the sum of the rest, right? So I really only have 8 values that I'm free to vary. The 9th value is determined by the other 8. Okay, so in this case, we have 8 degrees of freedom because there's 8 values that we could play around with, and the 9th is determined by the remaining 8. Okay, so how does that translate back to contingency tables? Well, the reason we have a chi-squared with 1 degree of freedom in a 2 by 2, even though we're adding up 4 things, is if we fix the margins and we tell you one of the entries then the other entries are determined by that one entry in the table. So we only really have one value to play with in a 2x2 table if we fix the margins, right? So here we have 8 values to play with, and the ninth is determined by the remaining 8. So we have 8 degrees of freedom for our chi-squared. So that's kind of where the name degrees of freedom comes from. All right, how many values are you allowed to play around with, and how many are fixed once you've played around with those other values? Okay. So it turns out we can carry out this computation: 11 minus 30 squared over 30 plus 12 minus 18 squared over 18 plus all the way out to 9 minus 5 over 5. And we end up with a chi-squared statistic with 59 degrees of freedom. Sorry, excuse me. We end up with a chi-squared statistic of 59, okay? And it has 8 degrees of freedom. If we calculate this probability, the probability that a chi-squared with 8 degrees of freedom exceeds 59 is small, all right? And so this provides evidence that the data do not follow Benford's law, right? Does this mean the data were fabricated? Not necessarily, right? But they certainly do not appear, there's strong evidence that they do not follow Benford's law, so perhaps there's some suspicion, maybe we want to follow up a little bit more to look into this. Okay? Any questions about that cute little example? All right, or how to apply this in your real life? No. Right? So, what'd you say? Right, yeah, exactly. Like every week we should have like another law that's helpful for your life, right? The more that they help you with illegal activities, the better. But no, I don't have any obvious things that come to mind right away. But so that's Benford's law. Okay, let's go back to where were we? Okay, one quick thing to just make you aware of. I'm going to go through this sort of quickly because it's not really something that you're probably going to encounter very often, and it's something that's sort of better dealt with in a course on correlated data. But I wanted you to be aware that sometimes you will see data arranged in a 2x2 table, but you should not apply the techniques that we've learned about to analyze it. And I'm going to explain to you the type of situation where that might happen. Okay? So suppose we're in the situation where we're looking at breast cancer patients that received mastectomy followed by chemotherapy, and the design was a randomized design, but it was a randomized design done in a special way where instead of just saying we're going to recruit a bunch of people and we're going to take half of them and randomize them to one intervention, which would be chemo perioperatively around the time that they had the operation, and chemo perioperatively plus another 6 months of chemotherapy. Instead of just randomizing half the people to one intervention and half the people to the other, what this study did is it actually matched people before doing the randomization. So it said, okay, we're going to find pairs of people who are very similar to each other in terms of their age and cancer stage. We're going to form those pairs, and then within each pair, we're going to randomize one person to get the first treatment and one person to get the second treatment, right? So this design is a little bit, it's still a randomized design because we're still randomizing people, but we're forming these pairs first, and then within each pair, we're flipping a coin to decide who gets each treatment. Okay, so it's different than just saying we're going to take all the people who enroll in our study and randomize half to receive each, right? We do this pre-matching, all right? And this pre-matching is going to be important. The outcome is whether or not the patient survived 5 years after surgery, and we want to know whether the probability of surviving 5 years is different between the two treatment strategies. Okay, so it sounds like something that we would sort of like to be able to assess using some kind of contingency table, but when we arrange the data in a 2x2 table, we'll see that it doesn't really correspond to what we'd like it to. Okay? So let's think about a table that looks like this. So if we think about exposure versus disease, right? Our treatment is perioperative chemotherapy only versus perioperative chemotherapy plus an additional 6 months of chemotherapy. And our outcome is whether or not you survived or died. Okay, so you think, well, great. We could put the data in this thing. Say we have, 515 people who survived 5 years, 5 who died within 95 who, 515 who survived 5 years with perioperative only, 526 who survived 5 years with perioperative plus 6 months, et cetera, et cetera. The problem with this arrangement is that you could ask software to carry out a chi-square test with these data, right? It's not going to complain at you. It's going to say, sure, numbers are big, do my chi-square test, figure out what the odds ratio is, test whether or not there's evidence that the exposure is different from the disease, the exposure is unassociated with the disease. But the problem is that that test or that approach ignores the fact that the outcomes in our study are not independent, right? So everything that we've done thus far with these contingency tables assumes that the entries in the table are coming from people who are independent. But by virtue of having paired these people in this design, we now have pairs of people who are in some sense more similar to each other within pairs than they are to other people in the study. So we've got this dependence in the data, all right? So the problem is that what we have is if we think about the data in terms of pairs, not in terms of individuals, then we now have each pair contributing 2 observations to this table, all right? And we really ought to be thinking about these data arranged in pairs, not arranged as individuals, because it's the pairs that are independent, not the individuals within the pairs that are independent, okay? So either a z-test or a chi-square test, the standard stuff that we do is not valid with this particular kind of table. So all I'm trying to point out is that it's important to understand the study design and not just say, oh, 2x2 table, therefore chi-square test will work, okay? So it is possible to arrange data in this way. This is an entirely valid way of presenting the data, right? It's not an invalid way of presenting the data, but when you think about trying to test the hypothesis, you need to see whether the way that you're proposing to test it is consistent with the design, or the assumptions that you need to make in order to carry out the hypothesis test are matching with the design, all right? So another way you could do this is you could arrange data in the following way, which is to cross-tabulate the perioperative only and the perioperative 6-month treatment groups and say who survived 5 years and who died within 5 years within those pairs. And in this situation, what you're doing is you're tabulating the pairs. So you're saying there were 510 pairs of people where both members of the pair survived 5 years, right? There were 16 pairs of people for whom in the perioperative plus 6 months, the person who got the perioperative plus 6 months survived 5 years, but the person who had perioperative only died within 5 years. So there's 4 different arrangements, right? There are 4 different possible outcomes for each pair. It can either be survived, 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 died, died, survived, or died, died, right? And you're tabulating which of those outcomes occurred for the pairs, okay? So in that case, each pair appears only once in the table, and now the total N in your study, of course, was 1,242, but there's only 621 entries in this table because it's summarizing the outcomes of the pairs, okay? So I'm going to go through this very quickly because I don't think it's really core for this class, but you can devise tests to test whether or not exposure is associated with disease when you have paired data like this, okay? There's a couple of approaches. The main approach consists of looking at the arrangements of the possible outcomes. So this would be like, did you die? No, no, yes, no, no, yes, 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 right? Those are the possible outcomes that could occur for each pair. And each of those implies a difference in outcome between the treatments. There was either no difference in outcome if both survived or both died, right? Or if you died under treatment 1 and didn't die under treatment 2, that means it's like a win for treatment 2. If you didn't die under treatment 1, but you did die under treatment 2, that's a win for treatment 1, okay? And the test is essentially based on adding up the total number of wins for treatment 1 and comparing it to the total number of wins for treatment 2, right? So essentially you're focusing on the pairs which are so-called discordant, right, where you have a different outcome under the 2 different treatments, because the pairs where the outcomes were the same really contribute no useful information to telling you about whether the treatment works, right? If both people survived or both people died, they don't really give you any useful information. So you're focusing only on these discordant pairs, and there's a couple of different ways of handling the counts and comparing the number of discordant pairs. One approach is to use a binomial distribution. So you can basically say, if the treatments were equally effective, right, that's the null hypothesis, then you'd expect the number of discordant pairs that favor treatment 1 to be, that number would be about half the total number of discordant pairs, right? Because of the discordant pairs, about half would have a win for treatment 1 and about half would have a win for treatment 2 if the treatments were the same, right? If the treatments are different, maybe if treatment 1 is better, you'd expect more wins for treatment 1 than for treatment 2. Therefore, you'd see a departure from a binomial distribution with a probability of 0.5. Okay, so you can base it on this binomial. We're not going to worry about the details. You can also do a more kind of normal distribution CLT-based thing, which is called McNemar's test. Don't worry about the test statistic here. It turns out that McNemar is essentially being made obsolete by the fact that computers can compute binomial probabilities for like almost arbitrarily large numbers. So it used to be helpful in the old days when you couldn't actually ask for like what is the probability that a binomial, 1,162, 0.5, exceeds whatever number, whatever value. Those calculations used to be hard. Now they're easy. So McNemar's isn't as important. But really just for kind of name recognition and to simply illustrate or to make you aware of the point that there are study designs which will give you, categorical outcomes that you might want to tabulate, but because of the nature of the study design, you can't use the standard toolbox all the time to do the comparisons. Okay, so just watch out for anytime you see matching or multiple measurements over time, just alarm bells should be ringing and saying, I don't know whether I can apply the standard stuff to this, right? I should take 74-30 statistical methods for correlated data, which I, up until next fall, have been teaching. So anyway, there's your plug for 74-30 if you'd like to know more. Okay, so in the next 20 minutes, we are going to start on some of the material from week 11. And we are going to talk about correlation. All right. So, who's heard of the word correlation? Everybody, I hope. Right? Everybody's heard of correlation, right? Correlation is one of those words that gets thrown around a lot, and we tend to play very fast and loose with the word correlation. And again, statisticians are terrible at naming things and saying things in a precise way. Correlation is another one of those problems. We tend to use the word correlation, as we'll talk about, to mean both the quantity that we are trying to estimate and the actual estimate of that quantity, just like we often use the word mean when we're lazy, and the mean is really the value out there in the universe that we're trying to estimate, and the sample mean is what we use to estimate it. Same thing with correlation, right? The correlation is actually a thing, right? It's a property of our data, and we try to estimate it using the sample correlation, but we often use the word just correlation to refer to that sample correlation, okay? So we'll try to kind of disentangle some of that stuff. So it's just to sort of take a step back and review what we've seen so far and to think about the nature of the variables that we have and what we can do with them. So what have we seen thus far? Well, we've seen that if we have a continuous variable and we either want to summarize that continuous variable within one sample or compare the levels of that continuous variable between two samples, we know how to do that, right? So that's like a t-test or a z-test or whatever approach we choose to use. So we've seen continuous variable, like we want to compare blood pressure between a group that got treated with the drug and a group that didn't get treated with the drug, and we're measuring blood pressure in this continuous scale. we can do some kind of comparison of means, right, between groups, or we want to look at the blood pressure within a particular sample and say, well, does the blood pressure for that population differ from some reference value? That's a one sample t-test. We've seen how to do that, right? If we have binary variables in one or two groups, right? So whether or not you got Zika, if you got vaccinated or didn't or whatever, then we can either do a Z-test, right, a two sample or one sample test of proportions, right, which sometimes is going to be equivalent to a chi-square test, right? So we can arrange things in this 2x2 table and do things using this contingency table chi-squared approach. And we also saw that as an extension of the chi-square test, we could deal with categorical variables with multiple levels. So at least if we're interested in testing homogeneity, right, whether or not there's any association between a particular categorical variable and some other categorical variable, if we can arrange them in some kind of contingency table, and all we're interested in talking about is the presence of any kind of relationship between these two variables, we can also carry out a chi-square test to do that calculation. So that's what we've seen so far. What we haven't seen is how to look at relationships between two or more continuous variables, right? We've got like age and blood pressure, or cholesterol and BMI, or something like that. So we've got two variables which are measured on a continuous scale, and we want to assess the relationship between them, right? We're not willing to take one of those two things and dichotomize it so we could do like a two-sample t-test, right? So you could always say, well, I'm interested in looking at the relationship between age and BMI, but I only know how to do t-tests, so I'm just going to chop my age and say, well, I'm going to consider people who are under the age of 40 and over the age of 40. And I'm going to compare the mean BMI in people under the age of 40 and over the age of 40, right? Well, that's certainly a thing you can do, right? If you only know how to do a t-test, right? If you got a hammer, everything looks like a nail, you can, change your question and say you want to do that, but that's not always the best approach, right? Sometimes you actually want to understand the full spectrum of the relationship between two continuous variables, right? And that's where this notion of correlation and then leading in to the idea of linear regression is going to come in. So here's some data that comes by default with R. It's called the air quality data. And so it measures a bunch of variables on a bunch of days about sort of atmospheric conditions. We're going to isolate three of these continuous variables, which are wind, temperature, and level of ozone, okay, that's measured on these days. This is not the full data set. I think I don't even know how many observations the full data set has, maybe something like 100 or something like that. But this is just the first 6 observations, just to give you a sense of kind of what the data look like. And so we might have questions like, are wind speed and air temperature related? Are the ozone level and temperature related, etc. So, one thing to note here, of course, is that, these temperatures are measured these temperatures are measured in integers, right? They're measured in whole numbers, right? So is this, strictly speaking, a continuous variable? Can it take values in between 72 and 73? In the data, no, it can't, because we're recording it as integers. But in theory, we sort of believe that the underlying variable of temperature is continuous, right? If you could measure temperature precisely enough, you'd be able to measure a temperature of 73.76216 degrees, right? That's potentially different than 73.7215 degrees, right? If you had a precise enough instrument, right? So even though we actually have sort of a fixed number of values for temperature, we don't have an infinite number of possible values for temperature in these data, we view it as a continuous variable. So that's when you talk about continuous, it's something that we sort of imagine underlying the actual data that we see is some kind of continuous process that produces continuous values, right? Values that don't have gaps between them, okay? So we have questions like, are wind speed and air temperature related? Are ozone level and temperature related? We're going to look at sort of all the combinations that we could possibly ask about here, just as sort of a toy example. Okay, so let's do something very basic. This is a scatter plot, right, of temperature versus wind speed, right? How do we produce a scatter plot? Well, we're going to take temperature and wind speed, and then for each variable, we're going to look at the wind value, and that's going to be plotted on the x-axis, and the temperature is going to be plotted on the y-axis, so that produces a scatter plot like this, what would you say about the relationship between temperature and wind on the basis of this plot? So A, is there a relationship? Does it look like there's a relationship? Yes, right? What is the nature of that relationship? They're like decreasing, right? So higher wind speed is associated with lower temperatures, okay? Would you say that it's like a really strong relationship, modest, moderate relationship, weak relationship? It's like modest, weak to modest, right? It's not like super strong. This isn't like, oh yeah, there's a definite, like there's clear, this wind speed is going to correspond exactly to this temperature, right? That's not the case. But there is some trend going on here. And what about the sort of the shape of the relationship? I don't know. It's kind of hard to see, right? It's not so easy to tell. I would argue that, you could, if you wanted to, you could sort of draw a straight line through this and say, oh yeah, it looks like a straight line would be a pretty good description. But if you told me that actually a better fitting line was something that was more curved, that sort of came down like this and then more sort of flattened out, I'd believe you as well, right? So it's hard sort of to tell the shape, right? So just some quick sort of code aside here. How do you get a scatter plot like this in R? If you're using ggplot, the way to get this is to set up your data here with this ggplot thing. Who's using ggplot for doing plotting in R? Anybody? No? Okay. People are just using plot. So there's an easy way to do this in R using plot. Anyway, okay, so we're not, if most of you have not really done ggplot, I'm not going to worry too much about this. No, it's not a big deal. No. This was just in the notes. I went with it. Are people just using, have people done plotting in R? No, you guys haven't done any plotting yet? Okay. Maybe a couple people have. All right. It might be something that you'll see in a lab, like maybe next week or something like that, or in a couple of weeks. So if you haven't seen plotting, then there's no point worrying too much about this. Okay. So as we talked about, of course, we can ask these various questions about this plot. Are the data well described by a straight line? How closely did the data follow this line? Does the line go up or down? Is the line steep or shallow? All those questions. The idea, actually, let me just show you a couple things. You could ask the same questions about this. This is the relationship between temperature and ozone. So what would you say is the most striking thing about this plot in terms of these sort of questions that I've asked about the plots? What's the thing that stands out the most here? So this is distinctly not a straight line relationship, right? It definitely looks like there's some kind of leveling off that happens above like an ozone level of about 100, right? So that's one thing I think that sort of stands out the most. It does appear to be a little more packed together, right? Maybe there's a little more coherence there, especially in the sort of 0 to 100 domain. Obviously, there's the sort of overall positive relationship between the two, right? We can look at things like this. This looks more like the blue plot. Maybe it's almost like a halfway in between the blue plot and the red plot in the sense that maybe there's a little bit of a curve here, a little less spread out than the blue. You can sort of look at all this exploratory stuff. This is not a variable that I gave you that I included in the data set that I showed you, but if you plot temperature versus day, and this is for one of the months that we have, there's not much going on, right, for this relationship. Now, if I looked at day over the year, right, what do you think you would see? Do you think you'd see a pattern? Right, you see, right, summer would be high and then it would go down. Of course, that wouldn't be a straight line either. It would be some kind of wave, right? But this is for 1 month, so maybe there's not a super strong relationship between day and temperature. I'm assuming here the reason we have more than 30 points on this plot is because on every day we took more than one measurement. So if you were actually analyzing these data you'd probably want to account for the fact that you have sort of potentially correlated observations over time, et cetera, et cetera. Okay. So there's lots of different relationships that we can try to intuit about these kinds of associations. But the idea that we're going to be talking about today is that we've got all these different dynamics going on here. We've got whether or not the observations follow a straight line, whether or not there appears to be a strong relationship between the variables, whether or not that seems to be positive or negative. So there's a lot of different ways we could describe these relationships. The correlation is a way of using one number to express the relationship between two variables. So we're going to take all the dimensions that we've talked about and sort of collapse them down to a single number that we're going to use to describe the relationship. Now, is that a good thing? It's got advantages and disadvantages, right? On the good side is now you've got a single number, which sort of tells you about, it represents the relationship between any two variables, right? You can say the correlation between ozone and wind speed is something. So you've got that single number. You can carry that single number around and say, that's my number that I'm going to use to represent this relationship. But of course, like anything, when we simplify, we lose information, right? So we're going to be losing information in the process, but we're giving ourselves a simple summary to do it, okay? So that's the idea, is to collapse down these various dimensions into a single representative number for a relationship between two variables. And the way we do that is using the correlation coefficient. So the thing that we typically call the correlation is really appropriately referred to as the Pearson correlation coefficient, all right? So it's named for this guy Pearson, who was also active, I think, in the in the early 1900s. This is to distinguish it by something called the Spearman's correlation coefficient, which you're not going to have to worry about. But the Pearson correlation coefficient is and I'm going to emphasize the word parameter here. Okay, it's a parameter, just like the mean is a parameter, the variance is a parameter. It is a characteristic of the universe that is generating our data, right? So the correlation is a characteristic of the process that leads to our data. Okay, so it's something that is fixed by assumption, but we don't know what it is. So we're going to try to estimate it on the basis of data. Okay? What we're going to be talking about in a little bit in a couple slides is that the key thing is that the Pearson correlation coefficient describes the linear relationship between two continuous variables. Okay? The idea that it represents the linear relationship is very important, and it is one of the things that allows us to collapse these multiple dimensions of describing an association down into one number, right? Because we said one of the things which describes the association is whether or not it's well described by a straight line or not. The correlation coefficient says, I don't really care whether the data are well described by a straight line or not. I'm just going to describe the straight line relationship, right? I'm going to say, what is the straight line relationship between these variables, right? So for example, going back to these red dots here, where we said a straight line doesn't necessarily describe these relationships well, the correlation coefficient says, I don't care. I'm just going to describe the straight line relationship between these variables, right? So you don't have to worry about describing whether the relationship is linear or not when you just say, well, I'm just going to describe whatever the linear relationship is. Okay, and we're going to see that the fact that it describes the linear relationship has some implications for how useful it is when data look certain ways, okay? Or for certain kinds of data. Typically, we denote the correlation by the Greek letter rho. So whenever you see this thing that looks sort of like a cursive lowercase p, which is rho, that almost always is referring to the correlation coefficient, okay? So if people refer to rho, then we sort of generally agree that that is referring to the correlation between two variables, okay? Here's the sort of mathematical definition or statistical definition of what the correlation between two random variables is. It's the expectation of x minus its mean times y minus its mean divided by the product of their standard deviations, right? Not super enlightening as to why that should summarize the relationship between two variables, but we'll get to a little bit later some intuition for why this formula makes sense, or this definition makes sense. The key thing, or another key thing to know about the correlation coefficient, is that it is a scaled value. Okay? So a scaled value, so it always takes on values between -1, which is perfect negative correlation, and 1, which is perfect positive correlation. Okay? So by scaling, by being a scaled value, again, it's a way for this measure to not worry about the magnitude or the actual values of the two variables that you're looking at, right? So if you measure temperature in Fahrenheit or measure temperature in Celsius, that's going to result in a different slope for the line that relates these two things. So if you're reporting, the number of units of temperature increase that are associated with a particular increase in ozone, right? That's going to depend on the scale that you've used for temperature and the scale on which you're measuring ozone. But the correlation coefficient does away with any of that scaling and gives you a sort of a common value that just reflects the association between these variables regardless of how they've been scaled. Okay, so it's always going to be between -1 and 1. And a correlation coefficient of 0.3 means, in some sense, the same thing for all different kinds of associations, right? It reflects the magnitude of this linear relationship for any kind of variable, any kind of pairs of variables that you're looking at, right? 0.3 is 0.3 is 0.3 is 0.3. It always reflects, like 0.3 is like a modest amount of correlation, always, right? 0.9 is a large amount of correlation, always. -0.8 is a large amount of correlation in the negative direction, always, regardless of the variables that you're looking at, right? So the value of the correlation always has the same meaning in terms of representing the strength of the linear relationship, okay? Okay, so I think that's probably where I'm going to stop. Next week, we're going to pick up with some intuition for how this works, and look at some examples of why the fact that the correlation measures the linear relationship has some important implications.